basically, there's one of our member who is very busy right now, but except him, others done our job. So we basically done text 3 and text 4. I'm in charge of text 4. Text 4 is my part. Text 3 is for booster, and there is also text 1 and text 2 is for another member in our group. It's called Halip. And for collaboration part is for Marat, but Halib is kind of busy right now. And the member I told you who is very busy right now is Barry. So so he maybe needs some time. But I can maybe share our data.
Okay, go ahead.
Okay. And I merged the 6 CSV file into one. So like the model data CSV, because I think for the collaboration part, we need the same split, the same train and test validation split. So I merge all into one and split first. So everybody could use a same split. And for the outcome, we choose code Edge SD010, and for several reasons. First, it's available for many participants in the dataset. The N, what they call NHANES, and has 5 order category from 1 to 5. 1 means excellent, 5 is poor, which naturally with the multinomial logic model. And second is self-rated health. Is known for strong related to important risk factors such as like age, BMI, or some blood pressure, and some lifestyle behavior, something like that. So it's meaningful from a public health perspective. So the HSD 010, the categories are not extremely imbalanced in our data. So the model has enough observation in each class to learn some useful patterns. Maybe this is text 4. Like this, I split into several distribution. This is 20 to 39 age, 40 to 59 years old, or 60 plus. And this is the self-rated health. 1 is very good, like excellent, and 5 is very poor. So you can see that maybe young people is tend to self-rated excellent than 60 years old. But there's some still there's some young people seems their health is really poor, like me. Although I'm like 190 centimeters tall, but I mean, this program is killing us. The workload is super heavy. Oh my god. So
Not
for
this class.
me,
You cannot say that of this class. You cannot say that of this class.
not this class. This class is kind of funny. It's kind of cool, actually. I learned a lot from this class, but for other class, it is literally killing me. Maybe I'll rate it myself as 4, maybe. And for a student in our campus, I think the average outcome would be like 4.5 or maybe 4, something like that. So from my perspective, I guess the red and purple are the college student because it's in the range between 20 and 39. Yeah. And there's a lot of other outcome from my part, but I want to share in next week in a presentation. Like, yeah, other outcome I want to share in the next week. Okay. And for the text 3 is for Booster. I don't know if Booster here.
I am.
Okay, do you want to share anything like on your part?
I think most of a lot of the different things that we look at will be in relation to each other. So it's a little bit hard to start with test 3 to say how good is my model compared to others when I haven't really looked at the other models, given that we were presenting next week.
Okay, you guys present next week, no problem, no problem.
Yeah.
Okay.
Okay.
Thank you.
Okay. Present next week. Some progress, but slow down. Okay, good. Is group B here, guys? Let me check who's my group B. Group B, go ahead. Guys, group B, group B, group B, group B. We're missing group B. Nothing to report. Nope. Okay, is group C here, guys?
Yes.
Go ahead, group C.
Okay. So can everybody see my screen?
But you have to switch to the presentation window right now. We don't see the
of course.
Okay.
Wait.
Okay, looking good. No. Try to move.
Okay. Is that okay now?
Yes, you have the Nimish. Go ahead.
Okay. So good afternoon, everyone. Today our group will present challenge 4, focusing on the multinomial logistic regression using the NHA-NES dataset, and we will walk through 4 main modeling components here. So here's the structure of today's presentation. We start with a quick introduction and discuss how logistic regression extends to multinomial logic. After that, we'll move through each task of the challenge. Task 1, compare one versus rest with multinomial logic. Task 2, explore the regularization. And task 3 introduced Ordinal Logistic Regression, and task 4 we are going to present another kind of model. And finally, we will review the calibration in the multi-class setting. So first, why the multinomial logistic regression? So many real-world prediction problems are not binary, not like 0 or 1. Example including the health status, active choice, and insurance type. Binary logistic regression cannot naturally handle outcomes with more than 2 under the categories. Multinomial logistic regression, or we also know MNL, extend binary logic by allowing 1 equation per class, turning linear scores into the probability. By using the softmax function. This is a statistical foundation used in many machine learning classification models. So the binary logistic regression models the log odds of a single outcome. It uses the sigmoid function to map linear predictor into probability between 0 and 1. When extending to multi-categories instead of one log odds, we generate multi-logics, one of each class, and convert them into a probability distribution using the softmax transformation, just like the diagram we showed before. This shift from a single logic to multiple logic is the key conceptual transition into the multinomial logic model. And this is the softmax modeling. For the K categories, each category has a linear score. We let it as a function of X. So the softmax is converted by this equation, and each score represents the latent performance or utility. So the softmax transforms the related performance into a probability distribution. For the task 1, we're trying to use for this challenge, our preliminary example outcome is the self-reported general health status. Participants rate their health from excellent to poor, from 1 to 5, into 5-level scales, and 3 tiers code as the worst healthy. So response like don't know or missing volumes are removed, and this variables is particularly useful because it can be modeled both as multinomial and as ordinal, allow us to compare the method across the task. So in the task one, we compare 2 approaches to multi-class classification, one versus rest logistic regression and multinomial logistic regression. We evaluate both methods using accuracy, training time, and prediction time across several outcomes. And the goals is to understand why multinomial logic prove more coherent multi-classic probabilities. And here's the result. Across all the tests we test, multinomial logic constantly achieves similar or higher accuracy than the OVR, which is the model we want to compare. Importantly, the MML trained faster because it fits one unified model instead of K binary models, just like we just introduced. We try to change the 0 to 1 into a kind of the distribution of the probability. So the OBR takes longer at both training and prediction time. Overall, multinomial logic is more efficient and produces more stable multi-class prediction. This is our result for task 1.
Just a second. Okay, let's stay here. What do you do? So when you go here, right? So when you do binary, you do one versus rest, right? But there is the ambiguity, right? When you have multiple models. Yeah, you know what I mean? Like there is an ambiguity. What if you have multiple predictors that predict a one? Yeah, can you tell me how you do that? How you combine the prediction from the multiple models into a single prediction? So here you have the multi-logit, right? And then, so here you have MNLN accuracy, right? And you have overall accuracy, right? The overall accuracy is the one that you use by combining the binary models, correct? These OVR models, correct? So how do you combine the prediction from the different models? So an input comes in, right? And you have 5 predictions. They are either predicting 0 or 1, or whatever. There's pretty reliability, right? Of being in a certain class versus not being in that certain class. How do you combine those reliabilities? So in the,
I should ask our team group member to answer the question. So
is the question clear? Team member, is it clear?
Yeah, I think it's online now.
Is the question clear? Hello.
Because I'm the people who help them to do this part of the presentation, but I'm not the people to write the code.
Do you understand my question?
Yeah, but I don't know how they practically practically separated the classes into the binary binary analysis or something.
Is the member here?
So he's not in from the computer, but I will try to help him to answer. But should wait me some seconds.
It's a cute question. I mean, I think it's a cute question. It has to do with like probability, log odds. So it's a cute thing to think about. I'm sure we'll get there to some other group. But
So I'm also curious about how generally people solve this kind of a problem.
Of course. I mean, let me just talk while you wait, right? Because it's,
Okay.
You can think of it as a Venn diagram, right? If you have the three, think about the case with the three choices, right? You have the three binary predictors that says group A, non-group A, group B, non-group B, group C, non-group C. And of course, group A plus group B should be equal to non-group C, correct? And the same thing, like group B, yeah, you understand what I'm trying to say, right? Non-group B should be group A plus group C, and non-group C should be group A plus group B. So the prediction have to be made consistent according to this probability states.
Okay. I think.
Okay, we cannot be here for forever. What should we do?
Can we just continue, and I'll try to answer the question after when we're writing our report.
Okay. Go ahead, guys.
Okay. So next, we're trying to use the test 2, which is try to regularizing the multinomial logic.
Usual stuff.
So,
yeah.
So we try to introduce the regular multinomial logic by evaluating the three kinds of model, which is the L2, L1, and the elastic net. So for the L2, redistricts coefficient, but do not have set them to 0, and the L1, which is which perform feature selection by pushing some coefficient to 0. And for the elastic net, they're trying to combine the both benefit from L1 and L2 to stable the feature selection in a high dimensional settings. And here we examine how log loss change with respect to the regularized parameter C here. All models reach their lowest log loss around C equals to 0.1. And while all models, if C is too small, the model over-regularized and underfitted. And if C is too large, the performance deteriorates rapidly. And elastic net shows the smoothest and the most stable behavior across the setting.
Now, just stay here a second. Can you go back once? Do you have also the non-zero coefficient plot? You know, the coefficient amplitude plot?
Ethan, is the coefficient plot here?
No, I see log loss versus the Lagrangian value, right?
The log loss versus the C.
Yeah, C is the Lagrangian, right? So C is the regularization.
Yeah.
I want to see the amplitude of the coefficient, like as we see in class, right? You want to see the amplitude of the coefficients. Like see how many coefficients go to 0 as the C increases, right? Diciamo dei sema.
不太懂。
So how many parameters you have in your model? Let's say you have 20 coefficients, right? 20 whatever. Then you have the C axis, right? And you plot the amplitude of the coefficients. And as C goes to 0, then you see that with L1 regularization, the amplitude, some of the coefficients go to 0. You understand what I'm talking about?
I didn't actually understand what is the question.
So you on the y-axis you have the amplitude of the coefficient.
Yeah.
On the x-axis you have the value C, the Lagrangian. Then you have multiple curves, each corresponding to one of the parameters in the model.
Oh yeah, we have 3 models compared here. But
Yeah. My point is that you want to see that with L1, right? As C increases, you send the amplitude of the coefficients to 0. And with L2, you have a smoother decrease of the coefficients value.
Yeah.
So add the plot. Vediamo dei ma
I didn't like. I should I didn't practically like finish the text. I helped them to do the presentation and trying to present. So I should wait them to answer the question because
So is the guy that did this plot here in the call? I mean, because as we said, right, everybody should present their own part. If you present a part which is not your part, then you cannot answer the question. So
yeah,
I'm not sure why you guys ended up doing this. Okay, let's go ahead.
Or maybe you can give us one more chance. We can.
Okay, but you understand my point, right? Everybody should present their part to answer the question.
Yeah, people should present their own part. And we will try to recruit our presentation completely in next week.
Okay, go ahead.
And for test 2, we also use the try to plot the log loss distribution here, and we compare the accuracy and the mean log loss in 3 different kinds of models. And for the test 3, we're also trying to analyze the 3 categories, and we compare the 2 models accuracy and other parameters. Then yeah, we're trying to.
Don't rush. Okay, just go slowly. Don't rush. Okay. So let's go back to slide 18. You rushed out of slide 18. I don't know why. Ordinal logistic regression. Okay, start from here. Go forward. Don't rush, please. Go ahead.
Okay. So in text 3. In text 3, we focus on the ordered outcomes, like we validate the proportional odds assumption by measuring the variation of each predictor's coefficient across the threshold, which is 0.5. And H shown the moderate variation of each, while the gender and income shows a very small variation. All predictors fall well below the 0.5 diagnostic threshold. So this suggests the proportional odds assumption is reasonably satisfied.
Good.
And here we interpret the ordinal model's odds ratio. And incomes have a strong positive effect. Individually, with the higher incomes are much more likely to report higher education. So the gender has a minimum effect. And age has a negative effect. The older individuals tend to report lower education levels. Ordinal models are especially useful because this effect applies constantly across the threshold. And trying to compare the ordinal and multinomial models, the accuracy is nearly identical, like around 40%. However, the ordinal loss is noticeably lower, indicating a better calibrated probability. And also, the ordinal model used about half the number of parameters, making it more more nominous and reducing the overfitting risk. And this plot shows how predictors affect the probability of higher education. The X shows a downward trend. Older individuals have lower probability of higher education. I think that is also reasonable because they don't have enough resources to take a higher education at that period of time when they are young. And income shows a strong upward trend. The higher income increases the probability, and this monotonic effect are easier to interpret in the ordinal model. And here's the confusion matrix. The ordinal confusion matrix shows most prediction lying along or near the diagonals. So misclassification typically occur between adjacent categories, like for example, HS graduate being predicted as some college. So this pattern matches the expected behavior of the ordinary outcomes. And for text 4 and calibration, we haven't finished it completely, so we don't have enough plots. But for talking about only about the concept, this model is simply the multinomial logic model with a random effect added to each group. So instead of a single prediction beta, we model beta plus as a group specific adjustment. The small group shrink strongly toward the overall mean, while large groups have more freedom. This behavior partially cooling prevents the overfitting and improves the stability.
Very good. Any reason? Oh, go ahead.
Yeah.
Any reason why you're falling behind on the challenge? Was there some exam? Was there you guys were just busy? You're getting bored?
Like for example, like this one, we already compared the accuracy, but we haven't completely compared. So we plan to compare more than this, but we haven't finished the plots yet.
But just natural. I mean, there's no external reason why you're running late, right? It's just. Okay, just go ahead. Just go ahead.
Yeah. So we found that this model have a similar accuracy to the old models, but significantly better log loss and more stable calibration. And we're trying to show the plot later, like after maybe next week, after we recute our presentation again. But so overall, the structure proves the both uncertainty, estimation, and generalization. And we haven't finished the calibration here. And here's all the pre-presentation we have.
Very good, very good. Okay, I feel the struggle. Please, next time, everybody presents their part. Okay.
Okay.
So that you can answer the question. And otherwise, you guys do a better job next time. Okay. I know that you guys are having your own problems, so I don't want to bash you, but I understand. Okay, very good. Do you guys also want to present Group C? You also want to define a report from the previous one from last week? There was something missing from last week, right?
Yeah, but we didn't add anything yet, but we just like, for me, I done the research for the good host law last time you mentioned.
Yeah.
Yeah, so I think the good host law specifically will affect our PMF because like the PMF optimize the RMSE, but the RMSE stop reflect model quality. So that is what good host law affect.
Okay. Yeah. Okay, very good. Group B, come talk to me, Group B. Come talk to me. Group B.
Okay.
Hello.
Give me a second. I'm setting the screen.
Group B. Present on the stream. Group B.
Okay. Hello, we are Group B. Our topic is multinomial logistic regression from logics to structures. I
Go
responded
back. Go back. What's the name? What's the name again? Go back one slide. What is the name?
Yes.
Multinomial. Can you repeat?
Oh, multinomial logistic regression.
Excellent. Go ahead.
Yeah. Okay. Okay, I'm responsible for data set. Our data set is NHANES. It's a long name, so it's a short version of its name. And our standardized folders are SRC data, notebooks, reports, and data. We load NHANES by CSV format, and because I was use XRT, then it cannot run properly on our Colab notebook. So I use CSV data to run. And our target variable of BMI with 4 classes: underweight, normal, overweight, and obese.
Very good. Very good. Very good. Very good. Very good.
We handle
Did you follow a little bit the discussion over the BMI, how BMI is not representative, how people criticize the BMI? Have you followed a little bit the discussion?
Oh, you say about BMI?
Yeah.
As I know, the formula is your weight and divide your height square. Yeah.
But you know, it's very controversial, right? Because if you are full of muscles, if you are full of fat, you are both have a higher weight, so it doesn't account for body composition, right? So it's and also like go ahead.
And and we handle missing values. These score continuous features, one hard category of features, then perform a reproducible stratified trend valid test split with a fixed seed. Finally, we expose on unified metrics accuracy, log-less, real score, ECE, and MCE, so any teammate can evaluate consistently and put results to our notebook. And why I use CSV rather than SAS data or XPT is we deliberately switch to the CSV Faber. Is public, well documented, and realistic for BMI imbalance. But most importantly, CSV avoid black key SAS export parsing in Colab. So no broken headers or accidental HTML downloads. Yeah, that was a big trouble for HTML data because my Colab cannot load it. That keeps the owner pipeline robust. The data set is big enough to learn useful signals, but still fast to iterate, which matters when the whole team shares the same loader and metric. And our data set snapshot after cleaning, we have 5,847 labeled samples and about 33 engineered features mixing continuous and one hot columns. The BM target is 4 class, as I mentioned. Underweight is 111, accounts for 1.9%.
Wow.
And normal is 1,741, accounts for 29.78%. Overweight is 1,843, accounts for 31.52%. Obese is 2,152, accounts for 36.81%. So we can see there are lots of obese people, so they should care more about their health. Yeah.
Okay, but also as we were discussing, also the BMI is a little bit critical, right? I mean, also in Taiwan, have you ever gone to the doctor in Taiwan to get your BMI score? Did you get your BMI? Did you get your BMI?
Yeah, by daily life, if you go to the gym at school, you can use their tool to get your BMI.
So how is your BMI?
Maybe let me count. I'm a little bit forgot it. Let me see. Let me use about 21.
But what is the? But in which category is it? Is BMI? Okay. Let me check. What is
Maybe-
BMI 21? How is it? If it's
Maybe it's normal.
God damn it! Because I'm obese according to the BMI in Taiwan. I feel so bad, you know.
But you are but you are very strong.
But still, I mean, if I go to the doctor, he writes that I'm obese, right? So in the I will be in the last category, you know. So it's hard for me to go to a doctor and be called obese by the doctor, you know.
Okay.
Let me check. So what's your BMI again? 20 something? You said
21.
21. 21. You are healthy. Yeah. God damn it. I'm jealous. So I'm jealous. Okay. Go ahead.
Okay. And our feature space is here's an example slides of our feature space. Continuous variables include age and income to poverty ratio, categoricals, sex, race, marital status, education, and others are one-hot encoded. You can see typical dummy columns like R I A G E N D R and RIDRETH. Standardization is fit only on trend and applied to test. One-hot encoders are likewise fit on trend, so there's no leakage. And then this is the charts. Yeah. This bar chart confirms the label school. Obese is the largest group. Underweight is tiny. Two actions follow. First, we always stratify splits so the distribution is stable across tests. Second, we report calibration, not just accuracy, because probability quality matters when classes are imbalanced.
Very good.
And this and for the last is for my teammates.
Very good. By the way, why we switch? In order for my BMI to be normal, I should be 82 kilos. And I haven't been 82 kilos since I was 23 years old. After I started going to the gym, I gained like 5 kilos and I went to the overweight category. Very sad for me. Go ahead, guys.
Yep.
Just telling you my personal struggle by being called obese by a doctor. Go ahead, guys.
Okay, so next is my part. Next page. Okay. So my part is to compare the one versus all method and the multinomial logistic regression method. And the data set we use is the enhanced data set. And the problem is, should we use one versus rest or multinomial? And the task is to compare them using accuracy, log loss, and calculate the cost, like the training time and the number of parameter under identical data and settings. Okay, next page. Okay, this is the data set overview. And we use the enhanced data set with the 5-class self-rated health variable as the prediction target. So the pie chart shows a strong imbalance, as we can see. The middle classes dominate and the extreme classes are really rare. So this imbalance will influence how both models behave. And here we have the features. The features we use include age, gender, race, education, income, and BMI, and so on, representing both numerical and categorical types. After merging and cleaning, the final dataset provides a diverse representation of demographic and health-related information. Okay, next page. Oh, so the first method we have
I
the
see.
OVR, it's the one versus rest. So in a one versus rest strategy, we build one binary classifier for each class. Each classifier focuses on distinguishing its class from all others. Like the picture here. During prediction, we collect the scores from all classifiers and pick the class with the highest one. So this strategy.
Now go ahead.
This strategy is quite simple, but the models are trained independently. They do not share information, which often leads to inconsistent probability outputs. And in addition, computational cost scales with the number of classes, which becomes expensive as K grows.
So here you should, let's discuss this a second. This is the important part, right? So cost, can you go to can you add linearly there, right? The cost scales linearly with K. So the cost grows linearly with K, okay? Understood?
Okay. Yeah.
So now here, this is the distinction where this is the discussion I want to have with the previous group, but then we couldn't have it, right? So let's just focus on P1, P2, P3, right? So let's discuss this consistency in probability, right? So I'll write in chat. Okay, so we have the first model gives you P1, the second model gives you P2, the third model gives you P3. Is that okay?
Mm-hmm.
And your decision, right, is to choose max of P1, P2, P3, correct? Max.
Yes.
P1, P2, P3. Okay, good. So the point that I was trying to do before, right, is that here you write is not consistent, is that you should have the 1 minus P1 is equal to P2 plus P3. Do we agree?
Yeah.
And because this is the inclusion-exclusion principle, right? Did you guys discuss? Did you guys think how you could make it probability consistent? Did you have some thoughts about this? Like how would you compare, let's say, one rule versus another rule? Any thoughts about this? You can just say no, right? I just want to know if.
Sorry.
Because here you treat it as a pool of expert, right? You treat it as everybody has its own reliability, right? But as you saw before, right? If a class has very few entries, right, then you have a large imbalance in the predictor. Again, let's say your class 1 has one element, right?
Mm-hmm.
Then the predictor 1 is always going to say that it belongs to the known class, right? So it's equal to known 1. But then you have to account for the fact that class has a very small representative. So how do you account for the fact that the reliability of this predictor must be very low, right? So, yeah. I think you understand the problem. You didn't think about it. It's okay, but yeah, I just wanted to have this discussion. No problem. Go ahead.
Okay, sorry. Okay. So where am I? Oh, okay. So next page. Next page. So the second method, we have the multinomial logistic regression. And multinomial logistic regression trains a single model that outputs lodges for all classes simultaneously. And the softmax function converts these lodges into a valid probability vector. So because the model is optimized jointly, it can capture relationships among classes and produce more consistent and better probabilities. So even though scikit-learn parameterize its similarity to OVR, the training dynamics are fundamentally different and much more efficient since it only trains one model.
Let me ask you something. Why is it called softmax?
Softmax.
Why is it called softmax?
Why?
I mean, it cannot be by mistake that they call it softmax, right? Do you have any ideas?
Softmax. Why?
If I tell you,
okay.
if I tell you, then it's too easy. Okay, now I'll just keep it for the next group. Then you don't drop out of class. You stay in the call, so you see the answer from the next group.
Okay.
Go ahead.
Okay. So next part, we have my experimental setup. So to make the comparison fair, so we use both models use the same training and test bed, and the same features and the same processing steps, such as standardization. And one
thing.
Hierarchical. The only difference between the two models is the multi-class strategy. So we evaluate both models using 4 metrics: accuracy, log loss, training time, and the number of parameters. And this pipeline ensures the fairness and the fairness of the comparison. Okay, next page. Okay, so we have the result. These confusion matrices shows the classification behavior of both models. So both models perform well on the dominant middle classes, which reflects the underlying dataset distribution. However, OVR exhibits more scattered and irregular mistakes. Because each classifier is trained independently, it can assign conflicting probabilities or misclassify it into non-adjacent classes. And in contrast, multinomial logistic regression produces more concentrated and structured errors. This indicates that it better captures the relationships between neighboring health categories. And this difference is a direct result of joint probability modeling, which OVR does not have.
Yes and no. Yes and no. Yes and no. I think you asked ChatGPT to explain this to you, but the explanation is not. No, stay here. Stay here. Let me think about it a second.
Okay.
Because you can really see number by number, right? And it's interesting. It's interesting. Because in a sense, right? So, because you didn't think about this the way I wanted you to think about it, right? But in a sense, the OVR does the hard max, right? And your multinomial does the soft max. And here you can see that, yeah. So for example, let's go row by row, right? Row 1, they are identical, right? Row 1, they make the same number of mistakes. And this is because there are so few elements in this class, okay?
Yes.
Row 2, row 4, same story, right? They make all mistakes, so nothing to say, right? The fact that one gives 20 and 12 and the other one gives 19 and 13, it's both equal to trash, right? Then row 2, multinomial does better, correct? But there is a large misclassification error in both. Row 3, multinomial does better. Row 4, multinomial does better. Right? So you can say, you can say row by. But I just wonder about this so also here the misclassification, where you misclassify category 1 for category 2. It comes from the overrepresentation of category 2, right? Because it's the category with the largest one.
Yes.
Yeah. Okay. Good. I think it's good.
Okay.
Nice. I think there is a lot to see here. Very good. Go ahead.
Next page. And so here we have the metrics and computational costs. So in terms of accuracy, both models perform similarly. However, multinomial logistic regression achieves slightly better log loss, meaning its probability estimates are more reliable. And the most significant difference is the computational cost. OVR must train one binary model per class, which makes it more than 20 times slower in our experiment. And multinomial logistic regression trains a single joint model and finishes quickly. So, although the parameter counts appear similar due to the library's implementation, the training efficiency and consistency of multinomial logistic regression are clearly superior. And this supports the theoretical understanding that joint modeling is more scalable and more stable than independent binary training.
So here, I would have reported the F1 score, right? Because we had this big discussion about area under the curve, F1 score, precision recall. I would have put the F1 score because the F1 score should give a better gap between multinomial OVR. Is that understood?
Okay.
Put it in the report, please. Go ahead.
Okay. So next page. So here we have our conclusion. So in summary, both models can handle
where is the calibration? Where is the rest? Where is the ordinal one? Okay, only for this part. Okay, it's only for this part, right? Go ahead. You scare me.
So both models can handle the classification task, but multinomial logistic regression is a better baseline. So because it trains significantly faster, produces better probability estimates, and makes more structured predictions. Okay.
You guys scare me. I thought the presentation was over. Yeah.
No. We still have other crew members.
Very good. Next.
And I'm taking the part of parameter explosion of solving a problem of parameter explosion in the previous part. So in our model, every new feature adds a set of coefficients for every health class. This creates a massive model that is prone to overfittingness. It starts memorizing noise instead of learning patterns. So my goal is to fix this using regularization. Okay, next page. Okay, so to solve this, I implemented 3 specific strategies. The first strategy is reach, and which shrinks weights but keeps every variable active. And the next strategy is Lasso, which adds features but often does so inconsistently across classes. And also the strategy number 3 is group Lasso, that it is the advanced method which treats features as structural groups. So it forces the model to make a tough decision. Is income important for all health classes or none of them? If it's not important for every of them, it will delete the classes. Okay, next page. And now let's look at the results. There's a fascinating contradiction here that I want to highlight. So first, look at the bridge. It achieved the highest accuracy because it keeps all features, even the noisy weak ones. In difficult borderline cases, these weak signals act as tiebreakers, helping the model guess the right class just often enough to win on accuracy. And however, look at Lasso. Its accuracy is slightly lower, but its log loss is significantly better. This is not a mistake. This happens because Lasso removed the noise. And By ignoring big unreliable signals, Lasso avoids being overconfident about wrong answers. It gives safer, more reliable probabilities estimates, even if it misses a few hard classification calls. Finally, Group Lasso showed 100% sparsity, but it is actually not a mistake, but a significant finding. It proves that our basic demographic variables, just like age, gender, race. Sorry, dudes, are you?
Yeah. So I want to ask you a couple of questions.
Okay.
So here, what is the parameter that you choose? I mean, how did you do the parameter tuning for the Lagrangian? The weight of the regularization. What is the coefficient that you chose for the weight of the regularization?
Excuse me, can you speak louder, or because I cannot hear it clearly?
I cannot speak louder, otherwise I deafen the whole floor. But you have the objective function, right? It's gonna be your log loss plus a constant c time the regularization loss, right? So how do you choose this value c? Because as you change the value c, then you change the value of sparsity, right? So how do you pick c in order to obtain these results? Is it the same c? Is it a different c? What is the value?
For that, I have to look back to my code because I've done it a few days ago and I kind of forgot it.
Oh, yeah, it's an important question, right? It's a choice that you must have made, and I wonder how you did that choice.
Okay, maybe I'll do that in the final report.
Second question. Okay. Second question. How can it be 100% specification? If you say 100% specification, it means that all the weights of the input, they are set to 0. So the output of your predictor can only be a constant value. So how can it be 100% specification and have the best accuracy?
Because just like I have stated, if the class is not fit to all of the classes, they'll be deleted. So the characteristic I'm using is only like gender, races, and all of that tags. The model isn't considered useful, so it deleted all.
And so what is the model predicting? What is the prediction based on? If you erase all the features, so then the model is just predicting the average, and the average would be regular weight, right? So the prediction is a constant, right? You just predict one single value. Is that correct? Is that what you're saying?
Yeah.
And so if you predict only one value, you are correct 42% of the time. Because the average class takes 42%, right? So because if you are a regular weight, then you are correct 42% of the time, right? But then you see that there is something wrong in your in the way you set up your problem, right? Because you're not accounting for class imbalance, and so you're just saying, you know, if I always get the average, then the loss is always then I get the same. But then of course it's, you know, it's not compelling, right? I mean, it's like if you go to somebody, right? You go to a bank, right? And the bank tells you, what is the average income of my customers? And you tell them what the average income of your customer is 30K, 30K a month, and you don't take any of the customer data into consideration. Will the bank be happy with you? Will the bank want to hire you?
Yeah, let me think how to answer that question.
Yeah, I mean, of course, it's because you know, we have the discussion, right? Accuracy is not your god, right? I mean, you have to choose F1 score, area under the curve. I mean, there is, because especially here, because from Group Lasso, you could have done a few nice things, right? So anyway, you get my point, right? So if your predictor collapses, it's because something went wrong. Okay, so two things to answer: how you chose this regularization coefficient, and yeah, as I said before, F1 score, right? Try to address the class imbalance. There are many things that would have been nice to see. Okay, go ahead.
Okay, so I'm going down to the next slide.
Go ahead.
Okay, So the heat map shows the result visualized visually. So to the right, you see the graph is actually, let me clean up because it's just like it's 100% because the demographic signals were weak. Just like because I only feed a signal that is age, gender, poverty, and I forget
So you have so few.
yes.
You have
So
few
I have
predictions.
to. So if we want it to be useful, so that which means the result shouldn't be 100%. I should feed more labels inside, just like BMIs or
Yeah, because the more, because then you have some interpretability, right? Because already, like if you have 20 inputs and you use reach to just reduce number of predictors, then but here you already start with very few predictors. So when you apply something, then everything goes to zero.
yeah. But however, to the left, the schema is pretty dense, and for the middle one, the random selection, there's random white gaps, which filter noise, but it's messy. So, but the one should be the most useful is totally blank because the data feed inside is not strong enough. Okay, so next page. Next page, please. Thanks. So the key takeaway of these parts are the trade-off. We found that Ridge is the best hard classifier, but Lasso is the best risk assessor. And the reality check, the 100% traffic in group Lasso is a wake-up call. It proves that demographics alone are insufficient. So, and it needs more data and useful text. So to do that, to do a better model, we don't need more complex penalties. We need to use the structure of the data itself. Okay. Yeah, I think it's done with my part.
Okay, good.
So next, we focus on modeling our target variable education level. Education is inherently an order concept ranging from elementary school to graduate school. We compare two modeling approaches, treating this level as independent categories using N and L versus respecting their order with an ordinal regression model. Next page. So this is the
Finally, very good. Good, nice.
so regarding statistical efficiency, well, the NNL model shows a slightly lower AIC, indicating a marginally better mathematical fit. This comes at a significant cost. The NNL model requires 6 parameters to achieve this feat, creating high complexity. So in contrast, the ordinal model achieves a comparable result using only 8 parameters. Based on the principle of parsimony, the ordinal model is structurally superior as it captures the data's core patterns with half-the complexity. Okay, so next page.
Oh, and yeah, okay, let's see. So what is this AIC? What is this AIC? In the previous slide.
AIC.
Yeah, what is AIC?
I don't really know what is AIC.
Why would you know? You just ask ChatGPT and it tells you, right? Just tell me, is it higher better or lower better?
Lower better.
Oh, at least you knew that one. Very good, very good. Okay, go ahead.
Okay, let's see. So this page, yes. And after standardizing our variables, the model reveals career drivers of education. Family income Family income is the strongest determinant with a coefficient of 1.06. This is more than 4 times the impact of age, confirming that economic status is the primary driver of educational attainment. Furthermore, the result reflects real-world demographic trends. The negative coefficient for age indicates that younger generations generally have higher education level than older ones, reflecting the expansion of mass education. Additionally, the data shows that males in this sample have slightly lower educational attainment than females.
You know that this is becoming a big problem, in the US, but I think generally also in the rest of the world, right? There is a gap between like males, they drop off of education at much higher rates than females. I think if we had to do the same statistic today, there would be a bigger gap. In some university now they reserve entrance for male because the amount of females it's larger dominates the faculty. Yeah, go ahead.
Okay.
Did you know about this?
Huh?
Did you know about this? That the graduation rates of males are falling?
Yes.
But you're gonna graduate, right? You're gonna graduate. You promised me.
And next page.
My jokes fly so flat. Go ahead.
So this is predictive probability plot. Is the probability plot is the core output of our ordinal model. The x-axis represents family income, poor to wealthier, and the y-axis represents the probability of being in a specific education level. So looking at the purple line, is the lower less than 9th grade. We see an exponential decline as income rises. For the poorest families, the probability of low education is nearly 30%, highlighting the strong link between poverty and lower attainment. In sharp contrast, the yellow or green line is the college grade graduation. Shows a dramatic sigmoid rise. This curve clearly quantifies a key insight. Economic resources are the essential tickets to higher education. This visualization demonstrates the ordinal model's advantage. Unlike the NNL model, which might produce erratic or crossing lines due to data noise, the ordinal model enforces monotony. It tells a consistent logical story. As resources increase, the probability of higher education consistently rises. This most intuitive predictive compatibility is crucial for career decision making. Okay, next page. Finally, we validated the model using the proportional odds assumption trap.
Very good.
Ideally, the impact of a variable should be consistent across all education levels, represented by horizontal lines on this chart. And observing the green line is the income. We see an upward trend. This indicates that income is stronger. It's a stronger differentiator for early education than for basic education, reflecting that economic barriers are higher at the university level. Although this slightly frustration strictly violates the parallel assumption, the direction remains consistently positive. The line stays well above 0. And so using an NNL model here will result in scattered coefficients that obscure the main trend. Therefore, we accept as the ordinal model. It effectively captures the robust positive relation between income and education, providing the most actionable insight. Okay. Next.
Conclusions. Okay, just for you, make sure that you if the vocabulary of what you want to say does not match what you. Yeah, I mean, you pick the vocabulary of your presentation was, I think, over your confidence level, right? So next time, try to use a simpler vocabulary with which you're more familiar, okay? Because if you struggle saying the words, I also struggle understanding them, right? Okay, next one.
Okay, so I'll talk about the hierarchical modeling and calibration. Next slide, please.
So I want to see finally some calibration, right? Because you guys, you all avoided calibration so far. That was the core of the challenge, right? So go ahead.
Okay, so first I'll talk about the objective. We are going to build a hierarchical version of the multinomial logistic model and compare it with the pooled baseline, and also evaluate and improve probability calibration using ECE, MCE reliability diagrams and temperature scaling. So why is hierarchical model? In health-related data such as NHANEs, different subpopulations naturally exhibit different distributions, especially with respect to age. Younger adults and older adults have very different baseline health profiles. A pooled model assumes everyone comes from the same distribution, which ignores real heterogeneity across groups and can lead to biased prediction, also often causes miscalibration, especially overconfidence. A hierarchical model solves this by allowing group-specific baselines while still sharing information across groups through partial pooling. So this makes the model more realistic, more flexible, and ultimately more in line with how health outcomes truly vary across the population. And the challenge in this data set is that yes, the Kaggle NHNE dataset contains only one survey cycle. A classical Bayesian hierarchical model is not feasible. And I will talk about the solution in the next slide.
Okay.
Okay, and what we will compare is that we then evaluate both models using calibration metrics such as ECE, MCE that I just copied. Okay. Next slide, please. One slide back, please. Yes. Okay, this is our data set, and we use the NHANE's demographic and questionnaire files, resulting in roughly 5,000 valid samples.
5,000.
And the target variable HSD010 encodes general health from excellent to poor, and we remove invalid responses. So, and then after that, we map it to 0 to 4 for multinomial modeling. Our features include age, income to poverty ratio, gender, and race, all properly encoded. Because SDDSRVYR takes only a single value in a Kaggle dataset, we cannot use survey cycle as a hierarchy. So instead, we create age group by dividing age into quintiles, which provides meaningful subgroup variation and aligns with known health difference across age groups.
Give the footnote.
This group variable allows our model to behave like hierarchical multinomial logistic regression. Okay, so next slide, please. So this shows the reliability diagrams before any calibration. The pool model's curve almost stays on the diagonal, which means its predicted probabilities naturally match empirical accuracies. The hierarchical model, however, shifts below the diagonal in high confidence bins, indicating.
Sorry, what is here the pooled one? What is the pooled one?
left one.
Huh?
The left one is a
Yeah.
pool one.
And what do you mean by pool here? What are you pooling?
You mean the data I'm pulling?
Huh? Come again.
Okay,
it's just one big pool instead of being hierarchical. Okay, it's the regular model, right? It's the regular multinomial logistic, right?
Yeah.
Okay, go ahead.
Okay, and the hierarchical model, however, ships below the diagonal in high confidence bins, indicating overconfidence.
Just a
This
second.
behavior.
Just a second. What are the dots here? What are the dots?
I'm not sure how it makes dots like this.
Because in one you have 3, the other one you have 4. So I thought it was the categories.
I think maybe I
Because
should.
you have 4 labels, right? No, you have 5 labels. You have 5 labels, right? So you should have a certain accuracy and confidence per each label, correct?
Yes, I have 5 labels.
So if you have a certain confidence per label, the confidence should not change according to the model. Sorry. Yeah. Oh, wait. Okay. So it's possible that the points collapse, right? It's possible that you have 2 points collapsing because the model changes both the accuracy and the confidence. I think that's what is happening, right? That some points they collapse, but they don't look collapsed. Go ahead. Go ahead. Do you know what's happening?
I think maybe I should check the code. Or
why check before the presentation? Always check after when I ask you a question, right? Go ahead.
Okay. This behavior is expected because group-aware models introduce additional flexibility through age-based group effects. And next slide, please. Okay, and this is the results after applying temperature scaling. The
Do you want to
hierarchical.
explain to people what is temperature scaling?
It's like
Go ahead.
It's like make the result more confidence by.
What the heck? Come on, you have to be specific. Like, what does it mean? Yeah, what is temperature scaling? It's a way of solving the problem. Yeah, of course, but how do you solve the problem, right? Well, what is the temperature? What is the temperature? The temperature is a parameter of what? Don't tell me you have to go check the code, otherwise I go hunt you down, right? Where is the temperature? The temperature is in which function?
It's by divide a parameter t on the logic of a model, and that will make the, like, for this part, the t is smaller than 1, and that will make the probability more sharper and more confident.
It's in the softmax. It's in the softmax. You have to say it's in the softmax, right?
Oh.
The softmax takes a vector out through the probability, and the t is in the exponential of the softmax. That's the answer that I want.
Oh, okay.
Right, because if you look at the softmax, it's like you can tune the sharpness of the softmax. By the way, why is it called the softmax? Let me ask you. Why is it called the softmax?
I also don't know why it's called softmax.
Guys, you cannot be so unthinking, right?
Yeah, I'm not sure why it's called so.
So disappointing. So disappointing. So disappointing. Go ahead.
Okay, so the hierarchical model improves, and its reliability curves move toward the diagonal, and both ECE and MCE drop noticeably. And
Do you have the value of the tau? Do you have the value of the tau after that you choose for the temperature? Do you have the temperature values?
I think it's below. It's just under the graph.
Under what?
T equals.
There. Okay. So the temperature scaling is very good. That's your tau. Good. Thank you. I didn't notice it. Nice.
Okay, and
So the tuning is minor, yeah, it's just minor tuning, but the effect on the hierarchical is very good. Okay, good. Go ahead.
and the pool models shows only slight improvement because it was
I mean,
already
it didn't
well.
improve. It didn't improve, right? It didn't improve.
It didn't improve, and in fact, the time scaling slightly overcorrects some bins for a poor model. Okay, next slide, please. So this is the summarize of the calibration matrix. The poor model is inherently well calibrated as shown by its low ECE and MCE before calibration. The hierarchical model performs worse initially, reflecting its greater flexibility. Temperature scaling significantly improves the hierarchical model, reducing both ECE and MCE. For the poor model, time scaling slightly lowers ECE but increases MCE due to overcorrection in certain confidence bits.
Can you tell me why calibration is important before, like, can you tell me, a little bit, why is it a big deal? Like, in your own words, right? Why is calibration something that we should be concerned with?
It's like the probability sometimes is not doesn't show that in the real world, and it does matter that the probability have to match with the one happens in the real world.
And why is it difficult to calibrate? Tell me, why is it difficult to calibrate in your mind?
Why is difficult? I'm not sure, but maybe it's because there are many things to consider.
The heck? You give me this answer. They are so vague. There are many things to consider. I'm not your mother. It's you don't have. I mean, you have to talk specifically, right? I mean, well, there are many things. Life is complicated, you know. Life is a journey. What's you gonna tell me next? You have to take the life each day. No, I mean it's like this, right? So you have, we say you have K predictions, and you have K labels, right? So in a sense, you have a joint distribution that you're trying to match, and the joint distribution grows as a joint matrix, right? As a joint probability distribution, where you have K labels for the prediction and K true labels, right? So this grows as K squared. So this grows as a quadratic function of the number of labels that you have. Okay.
Okay.
And this is really bad, right? It's really bad because the size of the matrix grows very quickly. So you can imagine that if you have two labels, right, then your matrix is a 4x4 matrix. If you have 100 labels, then you have 10,000 entries. And how can you pretend that with, let's say, 16 parameters or whatever, you are able to match a joint distribution with 10,000 entries, right? So that's why it's difficult.
Oh.
Does it make sense?
Yeah.
Is it a better answer that I told you if I told you, oh, because life is difficult?
Yeah.
Good.
Okay, so the hierarchical model, while more flexible and better at capturing subgroup differences, suffer from poor row calibration. Temperature scaling substantially improves its reliability and turning it into a well-calibrated group-aware model. And next slide, please. This is our team's work distribution.
Okay, so you guys worked well together. Did you cooperate? How was it? I said, how was the interaction in the team? Was it okay? Did you guys struggle? Nobody. Yeah, go ahead.
Okay, I'll answer it. I think we worked it quite well this time, and we got some problem that some slide was deleted accidentally last time, and some code is not working well after other people changed their parts. But this time our team leader make some backup code and also also put some slide that tell us where which part is for each person. So there's no any accident happen this time.
Very good. Very good. Very good. Very good.
Yeah, and I think we with distribution distribute the work quite fast each time.
Right. Yeah, because for me the final task, the calibration task, I didn't want to be only about the hierarchical model. I wanted you guys to consider all the previous techniques in order to do the calibration, right? So I wanted you guys to be like, oh, if I use a regular model, then this is poorly calibrated. It's poorly calibrated because, for example, some of the classes are very few entries, so I can use these different techniques for doing the calibration. So for me, the calibration task was a little bit more general on how you guys did it. Such is life. What would you say? What would you say? Things are complicated. Okay, very good. Let's take a brief break. Let's just do 5 minutes. So I'll see you back at 15:03, and we'll go with the next group. Okay, guys, I'll see you back in a jiffy. Ciao, ciao. Hello, guys. Slowly starting back. We are looking at group D. Is group
Hello.
D? Hello, hello, hello.
So we have separated our job, and since we just did challenge 3 and we got group member issued like 2 weeks ago, so we basically have a weekend week this week. So we just separate our job, and everybody is working on their parts very well, and we think we can have a fully presentation next week.
Okay. The issue was why? Was it? Remind me, what was the issue? Sorry, too many things happened.
So
Yeah, go ahead.
So since challenge 3, we find our group members ourselves,
Yeah,
and so at the first, only Shiying and me was in the group, so we have to find others who doesn't have the group, and we finally find some 2 others people.
Okay.
Last week, so we finished challenge 3 last week. Yeah.
Nice. Very good, very good. Okay. Now my favorite group. No, I shouldn't say my favorite group. One of my favorite groups. So you guys will present next week, right? Present
Yeah.
next week. Group E, my favorite group. Group E, come.
Hello.
You guys
I
are
will share the screen in a moment.
my favorite group. I shouldn't have any favorites, but why pretend?
It's always good to be the favorite from the teacher.
Yeah. Your mom's favorite and my favorite, you know. At least you have 2 people that consider you.
Yeah. We will do our presentation about the PDS challenge. And my group member will now present the first part, like task 1. So let's start, I think. One moment, I'm not sure if he is here yet, but I will ask him.
I see that you guys are talking about normalizing the OVR estimate. Let's see.
Yes.
Because the group didn't do it, so I want to see.
Yes, we're presenting right now. So we're using the NHANES data with 5 categories of self-reported health. We merge demographics, labs, diet, exams, questionnaire, and medications, giving a realistic multi-class setting with heterogeneous predictors. And here the OVR method trained 5 completely separate binary logistic models, 1 for each health category, and in each classifier, the positive class is rare and the model sees a very imbalanced data set. And when we generate probabilities, each model outputs a value between 0 and 1 independently. Because of their independence, the predicted probabilities don't sum up to 1, and because they are not true probabilities, we must normalize them using the equation given here. And and this is a very
I mean, yes and no, right? Yes and no, because from this equation, you are missing. What are you missing here? So basically, the total probability matrix is gonna have. I mean, I wrote it in chat, right? So what I'm saying is that you are missing from this, right?
Yeah. Yeah. Understood.
Yeah. Okay. So you understand why this is not complete, right? Because from how it appears here, for example, going back to the example with 3 classes, it looks like you have P1, P2, P3. But then 1 minus P2 will have to be equal to P1 plus P3, but P1 plus P3 are produced by 2 other models. So this model is incomplete because it seems you only have 3 weights when actually you have 6 estimates that you have to fix, right? So you will have to be like Okay, you understand what I'm trying to say. So this equation is incomplete. So go ahead.
Okay. And in contrast, the multinomial logic model trains one single model jointly across all classes, and then it uses a softmax layer which exponentials and normalizes scores to probability, and all normalized to a sum of 1. It means for the multinomial logistic models, there will be no need for manual calibration, and it will generate a more meaningful probability vector. Yeah. Next. And these are the results comparison between the OVR and the multinomial logic model. So as you can see, both model has similar accuracy for both models, but the multinomial model is actually well calibrated and more efficient, in the sense that actually OVR requires 5 separate training passes and a longer computational time. Yeah, and multinomial actually learn all the classes all together, where it reduces the training time and at the same time capture class relationships. And therefore,
so here let me ask you. So the OVR here, which strategy did you take for combining? You also took just the max of the probability vector produced by the separate by the 5 separate models.
Yeah. I used the probability. Yeah.
I want to say something more interesting, but yeah. I understand that you guys went for the straight answer. Because I tried to write that part to be a little bit more inspire some thoughts, but I think I failed. Go ahead.
Yeah, and this is one of the motivation for the use of multinomial models for our future following tasks, because it's more efficient and more informative. Yeah, that's all for my part.
That's it. Only 2 slides. Go ahead.
Okay, so now for task 2, we implemented Rich and Lasso regularization to address model complexity and feature selection. So you can see from the table, both models achieved an identical predictive performance with accuracy of 42.2% and a log loss of 1.304. This suggests the optimal penalty strength was similar for both in terms of prediction quality. However, they differ significantly in interpretability. Rich regularization by its nature shrinks all coefficients but never sets them exactly to 0, resulting in a 0.0% sparsity. In contrast, the Lasso model set 5.5% of the coefficients to exactly 0, effectively performing automatic feature selection. So for production model...
Yeah, the same questions for the other group were like, which coefficient for the sparsification did you use, right? So how do you come to this?
Like, you mean which coefficient I remove, or?
Yeah, I mean, how do you come to the choice of the coefficient? Because usually you remember the group C, right? They had the curve, right, of the accuracy of the function of they call it the parameter C, right?
Mm.
How do you choose that parameter in this experiment? It seems there was a pretty low C, right? And the accuracy was, yeah. How do you choose it?
I think I removed the most insignificant coefficient out of all.
No, that's not my question. So as I said before, right? So there is the accuracy, then you have plus a C times the L2 norm of the weights or the L1 norm of the weights. And the parameter C, you can choose it's a hyperparameter. So you can say from 0 to infinity. So in this slide, you don't have that value. So I'm asking you, which value did you choose to give these results?
Let me check my code.
Because usually, right, you want to choose that parameter according to some choice, and that group before the group C, they chose it to get the best accuracy.
I believe I chose it for the best accuracy as well. Let me double check with my code first.
There's an awkward silence, guy. We just wait.
Yeah, I choose it for the best accuracy.
Yeah, it's a problem, yeah. It's a problem. And for the best accuracy, you only set 5% of the parameters to 0, which must be one parameter because the total model must have like what, 12 coefficients? How many coefficients you have in the total model?
I'm not very sure about the total number. Yep, I'm not very sure about the total number.
Yeah, because here again, the issue again is that the dataset is imbalanced, right? So this accuracy of 0.42, it's yeah. You follow the discussion before, right? So that's what my concern is, right? Because
yep.
I would have reported the F1 score and not the accuracy. Anyway, go ahead.
Okay, so let me continue. So for production model, especially in the domain like healthcare, the Lasso model is superior. We can confidently simplify the final feature set, improving model.
Can you slow down a little bit?
Okay, we can confidently simplify the final feature set and improving the model explainability and reducing the number of input variables needed for scoring. Next slide. So next and arguably the most crucial for clinical use was assessing probability calibration. So this answers the question if the model predicts a patient has 90% chance of poor health, is the true rate of poor health 90%? So our uncalibration Lasso model has a low expected calibration error of 0.0093, which suggests good average performance. However, it had a massive maximum calibration error of 0.8209. This indicates a server flaw. In one critical bin, the model was catastrophically overconfident or underconfident. So we applied isotonic calibration as a post hoc correction method as seen in the table. The calibration step unsuccessful.
So you say isotonic. What is this isotonic? What is this isotonic calibration? That's what you said, right?
Yep.
So what type of calibration is that? Can you explain it?
Basically, it's a non-parametric method used to correct or adjust the predicted probabilities of machine learning model, ensuring that they accurately reflect the true probability of event occurring.
I mean, what is the formula? Do you have the formula somewhere?
I don't have the exact formula.
Is it a linear transformation? Is it isotonic? What can it be? Isotonic.
It's like a minimum of the summation of weight times the pi minus pi cap square, subjected to constraint of pi cap smaller or equals to pj cap.
So it's a non-linear one, right?
It's non-linear. It's the optimization is a minimum of p1 to pn.
And you choose the parameters according to the. Okay.
Yep.
Okay. Very good.
So
Go ahead.
Continue. Okay, so we applied the isotonic calibration as a post hoc correction method. As seen in the table, the calibration step successfully to reduce the MCE from 0.8209 to a very acceptable 0.0849. This eliminates the catastrophic worst-case error, making the model reliable for risk stratification. The reliability diagram shows this visually. The uncalibrated lines deviate significantly from the diagonal line of perfect calibration in one region. After isotonic calibration, the line is put much closer to the diagonal, demonstrating that our confidence score are now trustworthy. That's it for my part.
Okay, moving on to the ordinal model. This model uses the proportional odds assumption, which allows it to learn one set of effects and adjust it accordingly to the thresholds, as compared to the baseline multinomial regression. I mean, model which has no constraints.
Slow down a little
requires
bit.
more
Slow
data.
down a little bit, please. Slow down a little bit.
Oh,
I
okay.
need time to think. I have
No,
no brain.
go back previous page. Yeah, comparing the results as shown, the multinomial model predicts 42.2% as compared to the ordinal model of 33.9%, which shows that the ordinal model has a lower accuracy. This may be due to the model using the same features across all thresholds, which makes it easier to understand but also less flexible and accurate. So the multinomial model also performs better in terms of log loss, which is as it has a lower log loss point as compared to the ordinal model. For this case, the ordinal model also has a worse MAE, possibly due to the proportional odds assumption constraint being too restrictive, causing jumps to be bigger when a wrong prediction occurs. Okay, so the biggest advantage of using this model is the amount of parameters used. The model uses only 44 parameters or uses 44 fewer parameters, which is 80% lesser as compared to the multinomial model, allowing it to achieve similar results with simpler tools and datasets. So this allows for the model to be less prone to overfitting, but also makes it harder to capture complex relationship and reduce accuracy in general, as seen in the results. Okay, next.
So you have a you have a
Sorry?
drop of, I mean, you have a drop of 80% of parameters. I mean, that's massive, right?
Yeah, that's the advantage, main point of it. So next, the proportional odds assumption test. Okay, for this, I split the data into four different categories, as shown as in the top part of the graph. As seen in the accuracy predictions, the split 2, which is lesser than 2 and lesser than equal to 2 or more than 2, has the worst, in a sense, worst accuracy, as it is like a hardest, is the most cut through balance as compared to the rest of the distributions. So it's,
which feature is this? Which feature is this?
Sorry? No, as in the split. Not as in the
feature are
feature.
you splitting here? Come again.
As
Which
in,
feature are you splitting?
is in all the features are split according to -2. The predictions wise prediction.
This is
that's
the
equals to 2.
health.
Yeah, predictions, not the features. Yeah.
Okay.
So yeah, so realistically it will be the worst prediction as it is cut through in the middle. So yeah, looking at the coefficient graph, coefficient values across the cumulative splits, feature 8, which is the alcohol consumption, has the highest coefficient variation around 1.13, which makes it the only feature that has a variance of more than 1. This is likely, I'm not too sure, but this is likely due to alcohol's health impact being rather non-linear. So in a sense, moderate drinking of alcohol may correlate to like a good health, while going past a threshold, a tipping point will cause heavy, in a sense, seen as heavy drinking and greatly affects the predictions, making it far worse and not as well. So this relationship may drastically cause the change and difference in the variable coefficient. However, nevertheless, the mean coefficient is around 0.421, which is below the 0.5 threshold. And this means that the assumption that each feature has roughly the same impact across health categories is reasonable, however, not perfect, justifying the use of the single coefficient vector in the ordinal model. Okay, next.
Okay, so now I'll be talking about the calibration. So this slide shows the baseline calibration results for ordinal logistic regression model. And the expected calibration error is about 0.19, means that on average, the model's predicted probabilities differ from the true accuracy by nearly 20%, which is quite high. And the maximum calibration error is extreme under uniform binning, reaching almost 1.0, meaning that in at least one confidence bin, the predictions are completely wrong. Even under quantile binning, the maximum miscalibration remains high at about 0.27. And the higher Breer score confirms that the probability estimates are poor. Overall, this result shows that before applying calibration methods, the model is severely overconfident and not suitable for reliable decision making. And the reason that the MCE is lower under quantile binning is because quantile binning distributes samples evenly across all bins so that each bin contains a similar number of observations. In contrast, uniform binning divides the confidence space evenly, which can create bins with very few samples. In such a sparse bin, contains highly confident but wrong predictions, the calibration error becomes extremely large, which inflates the MCE. Therefore, quantile MCE is usually more stable and more representative of the real model behavior.
Please,
Okay,
also
next.
for you, slow down a little bit. Slow down a little bit. This
Alright,
group has a speed that does not allow my brain to catch up. Please do it for me. Go ahead.
Next. Next slide. Yeah, this. So this table shows how temperature scaling affected calibration quality. And after applying scaling, the expected calibration error drops significantly, meaning the model's predicted probabilities become much closer to real-world accuracy on average. However, the MCE increase suggested that while overall probability estimates became more reliable, the worst-case miscalibration worsened in a small subset of confidence bins. The Breer score also improved, confirming that probability estimates become more meaningful. This demonstrates a trade-off between improving average reliability and maintaining worst-case reliability.
So here is temperature scaling. Do you have the values of the temperature just to understand the?
For that, I will have to check, but if I'm not wrong, check.
Yeah, because the improvement is not. Yeah, because you know that so one of the things in the challenge, right, is that there are these very unbalanced classes. There are very few samples, and if you have a very few samples, you just cannot address the overconfidence, right? So
the temperature is 3.0.
3.
Yeah.
The temperature is 3. The tau is 3.
Yeah.
That's because you saw the other group, the temperature. Yeah, because the behavior with the softmax with tau, it's very extreme.
Yeah.
I was saying the following. Okay, follow me because I think about these challenges, and then some of the things that I think you guys don't catch it. And it's my fault. Okay, so there is the people you saw it before, right? The people with very poor health. There are very few of them. Okay. So the statistics of that class, how can it be confidently estimated? Right? If you have 10 people and 3 are sick, it's not the same thing as having 10,000 people and 325 are sick, right? So you have naturally, right? You have much lower confidence because it's much fewer people in the class. Does it make sense?
Yeah.
So when we talk about this calibration, right? It really depends on the number of people that we have in a class. If the number of people in the class is low, then does it make sense to calibrate for the class? The answer is no, right? Because the law of large number didn't kick in. So what is the point of asking for the law of large number to kick in if what is the point of asking for the calibration to be perfect when the law of large number didn't kick in? Does it make sense?
Yeah.
So there is this aspect that when you think about this calibration, you should account for the class imbalance, right? Because trying to calibrate a model for which you don't have good statistics doesn't make sense. So this is what I wanted you guys to notice. Did you think about this?
No.
But now you go home and you think about it, right?
Yeah, all right. I'll update the report according to it.
Go ahead.
Thank you. Yeah, that's all for my part.
Okay, very good.
Wait 1 moment. Yes, I will put the small thing of the team or of the Google meeting away. But let's start with Bayesian hierarchical multinomial logistic model. We have implemented region as a grouping variable, like north, south, east, and west, and made a model with random interceptions for each region. For this model, we made use of the Bambi library to estimate a model using Markov chain, Monte Carlo. And the formula we used is health status is age plus by ME plus gender plus region, where age by ME and gender are fixed variables and region varies over time.
Wow, nice.
We run 2 chains with 1,000 draws and 500 tuning steps to allow for good convergence. As like the model won't be suitable directly, it needs first 500 data points to adapt to the new situation, and then from there on it can run suitably, and then from there on we have 1,000 more points to test with. Pooled versus hierarchical. Pooled is like everyone is one big group, so we don't filter on region. And hierarchical is we filter on region. We have added a totally random filter with region. As like we made we made how I don't come to the name, but like sorry, wait, one moment.
You can use try to use your native language, and we see if we can understand you.
Yes. Okay, I will move on like with other words. We made like a model to just predict random variables in for hierarchical, which adds a random region, and then we tested if the difference in region changed the outcome of the model. So if it's closer to 0 or if it's real. The outcome was that the ELPD difference was only 1.15, and the standard error of both models is around 17.5. So there's almost no difference between the pooled and hierarchical challenge, which means that our model like really shrink the data to the good values. Like we use shrinkage, so all the model shrinkage to outcomes like it's reasonable. So it will shrink as there are less data sets, and then it will shrink to the right values. So it won't use, so it won't overfit. And regarding the outcome of the ELPD difference, we saw that hierarchical model and pooled model are not significant different. And the code identifies regions as irrelevant noise. So that's
what is ELPD here?
Expected log pointwise predictive density. So it's like a log function to check how close it is to the real answers.
Got it.
Let's move on to the table. The table interpretation. As the table shows the effect of living in a certain region on health, as the confidence interval all contains 0, like you can see HDI 3% and HDI 97%. It all contains, it's like a confidence, you can interpret it as a confidence interval, and it all contains 0. So we can say that the hierarchical model assumes in all cases that region does not have any effect on health. The pooling code already assumed this. For this reason, we can use the pooling code.
Good.
And furthermore, we can see in the R hat, it's all 1. So that has the same definition. Task for model calibration. For the model calibration, one moment. Expected calibration was only 1.2%. Which is an excellent result, as it has a calibration error of only 1.2%. This means, as the model says, it's correct 50% of the time. It is actually correct 50% of the time, plus minus 1.2%.
Yeah, but you don't want to be correct 50%. I mean, the accuracy here is still 40%, right? So
yes, it's in this case, it's 38.5 and 39.
I mean, since the confidence is so low, then is it? I mean, do you really have to be concerned about confidence when your accuracy is so low, right? Of course, the 0.5 points is. And you understand my point. Go ahead.
Yeah. Furthermore, we did bin analysis. The model claimed to be correct for 37.7% of the time for the bins between 9.3 and 9.4. And it was correct 38.6%, so it looks really good. and for the bin of between 0.40 and 0.50, the model claimed to be correct 41.5% of the time, and in reality, it was correct 39.8% of the time. This was it for model calibration, and I think this was our presentation. The end. Yes.
Okay. Didn't you guys have a female member in the group? Am I mistaken?
Yes, she made with me we made together like the part 4, but she
she's not
couldn't
here today
attend because she had a job interview, I think, or something like that.
I see. Very good, very good. I remember because there are so few females that I cannot help but remember which groups they belong.
In this department, there aren't a lot of females, I think.
That there is an ongoing problem that we guys have. And
yes.
We don't want to comment too much on it. I think my attitude is to try to be mindful while being respectful. So.
Yes, it's difficult for the guys.
You can speak, I cannot.
Yes, you can.
Okay, very good, guys. It's not politically correct for me to express it. Of course, we wish it was a 50% class, right?
Mm-hmm.
That's all we always wish. Okay, very good, guys. Yes. Yeah, I think everything went well. I think there are a few things. Yes, I think a lot of the groups I wonder if I could have done something better to convey more the challenges in the class, in the challenge. I wonder if I could have done something more to convey the subtle point of the challenge, right? So one of the subtle points was this how to combine the confidence of the multiple model, this task 1, right? And the other one was the calibration, right? So this point of the calibration with the fewer class percentages and so on and so on. So maybe I could have done something better. But as I said, I try to keep the challenges very fresh, very based on the discussion in class and the presentation in class and what you guys have in your presentation. So I wanted to add to this because we had this discussion about the F1 score and the difference between accuracy and actual statistical performance of the binary model. So, okay, very good. I think for today we stop here. I will stop the recording now. So if you have any questions and you don't want it to be recorded for YouTube, you can do it now. Say hi to the YouTube viewers. And remember to subscribe. Yeah, whatever, comment and notification bell, whatever. Okay, so.